Hey guys, today I want to present a solution to the Japan Math Olympiad 2020 problem 3. At first, let's have a look on the problem statement. We are asked to find all functions from the positive integers to the positive integers such that m squared plus f of n squared plus m minus f of n all squared is greater than or equal to f of m squared plus n squared for all positive integers m and n. To get the best possible statement out of this inequality, we want to get rid of this term m minus f of n squared, because this only makes the left hand side larger, and therefore our first idea is to plug in m equals to f of n. So m equals f of n gives us that f of n squared plus f of n squared, which is 2 times f of n squared, is greater than or equal to f of n squared plus n squared. At this point, we directly see that we get a weird behavior if f of n is less than n, because then, in order to let this inequality be true, f of n must be less than f of n. This then leads to a downwards spiral, which is not good because we are working in the positive integers, and therefore the function values are bounded from below by 1. Therefore, we want to prove that f of n is always greater than or equal to n, and we do this by contradiction. So assume that there exists some n such that f of n is less than n. As I've already said, this implies that f of n is less than f of n. And now we can go on and say that this implies now that f of n is less than f of n, f of n, and we can go on to get that in total f to the power of k, which means that we take f k times of n is less than f k minus 1 of n. Moreover, since we work in the positive integers, this inequality here is equivalent to the inequality that the left hand side is less than or equal to the right hand side minus 1. And here we recursively get that this is less than or equal to fk minus 2 of n minus 2, and so on, and then this is less than or equal to f of n minus k minus 1, and this is less than or equal to n minus k. For k greater than n, this is clearly a contradiction, and therefore our assumption was wrong, and we can conclude that f of n is always greater than or equal to n. At this point, it would be nice if some similar argument can be done in order to prove that f of n is also less than or equal to bn. And therefore, let's try this out and see what happens. So assume that there exists some n such that f of n is greater than n, and this means we can write f of n equal n plus k for some k greater than 0. So let's plug this into the inequality here and see what we get for f of n. We get that f of n plus k squared is less than or equal to 2 times n plus k squared minus n squared. This is now 2 times n squared minus n squared, which is n squared plus 4 times nk plus 2 times k squared. Because k is greater than 0, we can say that this is strictly less than n squared plus 4nk plus 4k squared, and this is now n plus 2k squared. Since we work in the positive integers, we can take the square root of both sides and get that f of n plus k is strictly less than n plus k plus k, and here we can also say that this is equivalent to f of n plus k is less than or equal to n plus k. plus k minus 1. This inequality here means that if we find some n such that the difference of f of n and n is equal to k with greater than 0, then we can find an n prime such that n prime is greater than n and the difference of f of n prime and n prime is at most k minus 1. And intuitively, this directly implies that at some point we can find a big n, which is greater than n, such that f of large n is equal to large n, and we can make this formal using the extreme value principle. So let's choose capital N such that capital N is greater than n, and f of n minus n, which should be defined to be capital K, is minimal. And this is always possible because of the inequality f of n is greater than or equal to n. We know that the left-hand side is always non-negative and therefore bounded from below by 0. If k is now not equal to 0, we can do this argument here from above to conclude that the difference of f of n plus k minus n plus k is at most k minus 1. And since clearly n plus k is larger than n is larger than small n, this is a contradiction to the minimality of capital K. Thus we get that k is equal to 0, which implies f of capital N is equal to capital N. Here we can plug in capital N into small n in the original inequality to get that m squared plus capital N squared plus m minus capital N squared is greater than or equal to f of m squared plus capital N squared. Bringing the n squared to the left hand side gives us that f of m squared is less than or equal to m squared plus m minus n all squared. Here we see that if the difference of m and n is small, then the right hand side is nearly m squared, and this would mean that f of m must be equal to m because we have the inequality that f of n is greater than or equal to n. Therefore, we are motivated to plug in n minus 1 for m and get that f of n minus 1 squared is less than or equal to n minus 1 squared plus 1, and this is now equal to n minus n squared minus 2n plus 2. And now we remember that capital N is larger than n, and this means that capital N is at least 2, and therefore this is clearly less than n squared. This implies now that f of n minus 1 must be equal to n minus 1 because we have the inequality f of n is greater than or equal to n. Now we can go on inductively with the same argument up to the value small n to conclude that we also get f of small n is equal to n. This is a contradiction to our assumption that f of n is greater than n, and therefore this assumption must be wrong, and so the only possible solution to our problem is that f of n is equal to n for all positive integers n. Plugging in f of n equals to n in our original equation gives us clearly a true statement because we have m squared plus some non-negative term on the left hand side, which is clearly greater than or equal to m squared plus n squared. And therefore this is indeed a solution, and it's the only solution, and therefore we are done.